I am your host. All right. All right, now there is a wealth of information that actually appears on a titration chart. Way more than just, hey, we got to the pH 7, it's neutralized. Now watch. What do we start with? Let's say we're going to start with an acid. So we're going to say Ha is our acid. Okay? So we're going to start with all Ha. There's all Ha, and there might be a tiny bit of Ah. Now why might there be a tiny bit of Ah? It dissociates. Now, if it's strong acid, it's all dissociated pretty much, right? But let's say we're starting with a weak acid. If it's a weak acid, it's going to be Ha plus water in equilibrium with H3O plus Ah. Yes?
Yeah.
Okay. Where does the balance lie if I tell you the Ka is 1.8 times 10 to the negative 6th? What do you have mostly? Mostly reactants. So there's almost all Ha and pretty much no Ah. Aha. Now, so we're going to start at some pH. Okay? We're going to start to add base. So this is the volume of the base added. Now I know you saw a lot of this, but I'm reviewing because there's a lot of points on here. All right? So we start to go up. Now the weird bit is the pH doesn't rise very much for a very long time. Okay? That's the reason for that is because of what's called buffering. Yes. No error. All right. Okay, we'll talk about this region, this buffer region, in just a minute. Now, all of a sudden, it shoots up. Well, what's happening? What's happening to the amount of Ha? When the H is together with the A. Okay, whoa. Okay, I didn't get a neat universal answer there. So here's some water. Look, we're not going to draw the waters in, but it's Ha, right? I throw an OH into Ha. What happens? Ha plus OH makes what? Water makes a Ho plus Ah. Right?
Yeah.
Okay, so can you see that or is it?
Yeah.
There we go. Okay, so Ha plus OH makes water plus Ah. Right? So if we start with a bunch of Ha, what happens to the amount of Ha? It decreases. So it's like Ha, 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 Ha. Okay, now what's happening the other way? What's happening to the amount of Ah? Right, Okay, yeah, we get the idea. Now, we're not going to worry about the Ho because the Ho is just water and there's more water. We're adding water to the water. All right? Now, we're not going to go into all the implications that are possible there now. All right, moving on. Now, all of a sudden, what happens? It shoots up because what don't we have anymore? Which? Say that again. Ha. We got plenty of Ah. We're getting more and more Ah, less and less Ha, to the point there's no Ha. When we get no Ha, what happens to the pH? All of a sudden, what happens to this equilibrium? It's blown, right? There's no more equilibrium. And so all the H3O pluses are used up, right? Because there's a second reaction going on here. The H3O pluses that are in the water are reacting with the hydroxide that we put in the water, and what are we making? 2 Ho's. Right? All right. So the pH goes shooting up. Now, it'll start to level off again based on what kind of hydroxide we're adding here. All right? Because we're just increasing the hydroxide, so we're getting oh. Right? Because there's nothing to neutralize it anymore, and it's not neutralizing anything, so the O's are increasing as we go across here, and that's what determines the pH at the top. Now, some folks, she showed you a bunch of really important points. Thing number 1 is where it's totally neutral. Okay? That's actually, it's weird because that's actually the inflection point where this changes from one slope to the other. So when the curve goes from here to here, that's where it's neutralized. okay? If you graph this a couple different ways, there's some easy ways to find that point. That point will not be at 7. Okay? That point will not be at 7 if it's a weak acid or a weak base. We'll talk about that. Okay, now, as you're coming across here, right, what's happening to the amount of Ha? It's decreasing. What's happening to the amount of Ah? It's increasing. There's a point here where the amount concentration of Ha equals the concentration of Ah. Okay? If the concentration of Ha is equal to the concentration of Ah, right, that's going to be very, very useful.
Would that be where the pH is 7?
No. No, not at all, because do we still have a lot of Ha?
Yeah.
Are we still in this equilibrium here where we've got Ha's and Ah's?
Yeah.
Yes?
Yeah.
Okay. So that is not where it's pH 7, not even close. You notice where it is on the graph. It's not anywhere near pH 7. So let's see what is going on now. Here's the deal. Why is that particular point important?
Because it's a Ka.
Okay? Because that's where we can easily determine the following. Here, if we write the K for this expression, what is it equal to? Concentration of, everybody, come on.
Hydronium.
Hydronium.
And acid.
And,
A
base,
minus.
Ah, over
The acid.
Ha.
Ha. Right? Now, look closely. If these two are equal, if this is equal to that, what do? They cancel. Now it's only, please listen, if you forget everything else that I've said this period. This right here is the only point where this is true and these cancel. It's the only point where that works. So where you can find exactly where Ha equals Ah, then Ka equals the concentration of H3O plus at that point. Okay? Does that make sense?
Yes.
Now, are we okay with that? Now, here's the deal. We're not working in H0 plus cons, we're working in pH. Yes?
Yeah.
So we know the pH at that point. Well, we can take the P of both sides of this. We can take the pH and the pKa.
What's the pKa?
Okay, all that is, how did you find a pH? You took the negative of the log of the H0 pluses. Okay? pKa is the exact same thing. The reason it came into existence, truthfully, one of the things is because we're using such huge different range of numbers. The other reason is pKa is a whole heck of a lot easier to type in a book. You know, think about it. This could be 4.8 times 10 to the negative fourth. You know, and whatever that is, whatever that turns into when you make the pH, that's just like a 2-digit number. True? So you take all pKa is taking the negative of the log of whatever the Ka is. It's the same thing. Good so far.
What is
Yeah.
the pKa? Finding the pKa, what does that do for you?
Nothing. The only reason this is here is if you're trying to find the Ka, you're already here, right? You already got that because you go, here's where Ha equals Ah, that's the pH. So I've got this, which means I can get this, which means I can find that.
Okay.
Because I can un-P something pretty easily, right?
Yeah.
So
How do you un-P pH?
10 raised to the
10 to the
10 to the negative of the pH. Well, it's 10 to the negative of the pKa gives you the Ka. Jared?
So the only point in which pKa equals the pH is at that point.
where HA.
When they cancel.
Where, right, half, it's the half it's like the half equivalence point or the half titration point.
What's the purpose of pKa outside of that?
Like I said, other than to make it easy to put in a book. It just shrinks the numbers down. Because you think about it, your Ka values are going to be everything from 1.0 times 10 to the negative first all the way down, or times 10 to the negative 14th. It's a huge range of values. Only reason we did it was to shrink the values down into a reasonable size. Okay? Now, two other things, and then I'll let you work on the warm up or the pre-lab. Thing number one, why does this stretch, does the pH never go up?
It is going
It is going up, but you would think you're adding a ton of base. All right, you're putting OH into this thing, and the pH doesn't change hardly at all.
up.
Okay? This right here is why you're alive. It's also why, if you've ever run the 400 meters, nobody loves you right after you come off the turn. Okay? This is the buffer region. Okay, this is called a buffer region. Now give me a couple seconds, we'll do buffers. Could you kill that and we'll start again?